Students, we have started in the last classes the topic of the wave and now we are proceeding to the subtopic of the topic waves, that is called the stationary waves or the standing waves. To describe the stationary waves, first of all we will discuss about the some points from the previous lecture. For example, what is wave? Basically, wave is the phenomena, or it is the disturbance produced in the system by which energy can be transmitted between the 2 points. It is called the wave. And we have different types of the waves. For example, the waves in a water or the water waves, and waves in a piece of rope, and the waves produced in the string or the spring. These are the examples of the waves. And we have different categories of the waves already discussed in our classes, just like the electromagnetic waves and the mechanical waves. What are the mechanical waves? Basically, the categories of the waves which cannot be transmitted, which cannot transmit the energy without the medium. And the electromagnetic waves are the waves which can transmit the energy from one point to another point without the medium as well. For example, the light waves. Now we'll discuss about the stationary waves, especially. Stationary waves, basically it is the name given to the waves because of the rest profile of these waves. Because the stationary waves cannot be seen as the moving waves, their profile can be observed in the rest form. That's why these waves are called the stationary waves or the standing waves. How can we produce the stationary waves? Basically, it is a vibrator, and a string or the piece of rope is connected to this vibrator, and it is horizontally placed, and the other end is the fixed. And when we start the vibrator, it can move or oscillate vertically upwards and downwards, and the transverse waves will be produced in this string, which can be observed in this diagram as the black wave, that is called the incident wave. It means the energy is transmitted from left to the right, that means from point P to the point Q, and after reflecting back from that obstacle or the fixed point, that is Q, now there is a 180-degree phase difference between the reflected wave and the incident wave, and these reflected waves are also formed in the same region with the same speed, and both waves, those are incident waves and the reflected waves, have the same frequency because these waves are produced because of the same source, that is the vibrator, which is oscillating vertically upwards and downwards. That's why I am repeating here. The generated incident waves and the reflected waves are produced in the same medium, and they have the same speed, same frequency, and the same wavelength. Now, these incident waves and the reflected waves interfere to each other, and in the result of the interference, these stationary waves are formed. Now we have different observational points here at which the amplitude of the wave is maximum, and we have also the points on this stationary wave where the amplitude is 0, because these points are lying on the equilibrium position. Basically, where the amplitude of the wave is maximum, these points are called antinodes, and these points are the result of the incident wave and the reflected wave when the constructive interference occurs between the incident wave and the reflected wave. These are the antinodal points where the amplitude is maximum. And we know that where the amplitude or displacement of the wave is maximum, the energy level will also be maximum. But we have also other points where the amplitude is 0, and those points are lying on the equilibrium position. So that's why energy level will also be 0 there. And these are the points which are called nodes, and these are the points which can be produced in the result of destructive interference between the incident wave and the reflected wave. So it means we have two notations here the one is A and the other one is N. A stands for antinodal positions or the antinodes, where the amplitude is maximum, and energy is maximum. And we have other points which are denoted by N. These are called nodes. And at the nodal positions, the amplitude is 0. Or we can also say that the amplitude is minimum. And the energy level is also minimum. So basically we can describe the stationary waves, the waves by which energy cannot be transmitted. And how can we say it? Because we have the fixed number of loops for a particular frequency of the vibrator. If we change the frequency, the number of loops will also be changed. Means we have here the 4 number of loops, we have a particular frequency of the vibrator. If we change the frequency, the number of loops will also be changed. It means if we increase the frequency of the vibrator, the number of loops will also be increased. Now it means the more number of loops will be formed on the stationary waves. And energy is confined in each loop itself or individually. And if we move from point P to the first nodal point, the energy level is increasing and it is maximum at the middle position of the loop, and it is now getting minimum and it is 0 almost at the nodal positions. Okay, so energy of a particular loop is confined in this loop. Now we'll discuss about the properties of the stationary waves. First of all, we'll discuss about the wavelength, which is difficult to estimate from the stationary waves, and students have the difficulty in estimation of the wavelength. First of all, we'll describe the wavelength in the progressive waves for the repetition of our concept. For example, it is the horizontal string which is fixed from the one end and which is free to move from other. Now we are moving or vibrating this string or the piece of rope vertically upwards and downwards. A particular wave pattern will be formed that is called the transverse wave. And we know also that it is the position of the crust and it is the alternative crust. The distance between two successive crusts or the troughs is called wavelength. These are the positions, those are called troughs. So wavelength can be described in the progressive waves just like the distance between two successive crusts or the troughs. And we can also describe the wavelength in the form of the same phase points. For example, if we are considering this point A here, the alternative same phase point is B. The distance between these 2 points is also equals to the wavelength. Now we'll discuss about the wavelength in the stationary waves. For example, it is the incident wave and it is the reflected wave, and the stationary wave is formed. Now if we are starting from the point A, the one wave is completed up to the point B. So the distance between these 2 nodal points is called the wavelength. And we know that this formation of the stationary wave has a particular name that is called loop. It is a loop. And if we find or calculate or estimate the distance between the 2 successive nodes, for example, it is the first node and it is the second node, so this distance will be equals to the half of the wavelength. And we have also here the 2 other points, those are called antinodes, which are the middle points of the loops. In the other diagram we can describe it very clearly. For example, it is a position of the antinode and it is another position of the antinode. So if we find the distance between these two antinodes, it means that it is the half of the wave completed here. From point P to Q, the half of the wave is formed, so it is equals to the half of the wavelength. Okay, students? Now if we describe the wavelength of the half of the loop, for example, we are starting from this point, that is, for example, R, and it is a nodal point or the point S, and now we are describing the wavelength of this half of the loop. So it is equals to the quarter of the wavelength, because from this node point to this node point we have one complete wave formed here, so it is equals to the wavelength, and one loop has the half of the wavelength, so half loop has the quarter of the wavelength. Now we'll discuss about the movement of the particles in the stationary wave. For example, if we consider these number of elements, now we are taking the example of a string or the rubber band which is fixed from both ends. For example, it is a string just like the guitar, or the rubber band which is fixed from two ends, and these points are P and Q. Now we want to generate the stationary waves in this string. So we will plug this string from the middle point or the midpoint, and the new position at the time t is equals to 0, suppose we have like this. Now if we release this string or the rubber band, so it will start to vibrate and it will move vertically downwards, and the new position after a particular instant for this string will be here like this. Now this string starts to vibrate and a particular loop can be seen here, okay, because we have plugged this string from the middle point. Now at a particular point the position of the string will be upwards or the downwards. It cannot be possible that the same string is present at both positions, just like black position and the blue position. So it means that if we are considering here this string or the rubber band is consisting on particles, these particles are moving simultaneously or at the same time. For example, at the time t is equals to 0, all these particles which are on the black wave pulse are in the upwards direction, and when we release this string or the rubber band, they will move in the downward direction, and the new position of these particles will be on the blue wave. As I have told you that both positions cannot be occurred at the same time, at a particular instant there will be a position for the rubber band or the string for the black or the blue. Simultaneously it cannot happen. It can be present at the both positions. Now if we consider these types of the stationary waves, for example, it is a position of the wave and these are the nodes or the particles, and when we release it, this string will be moved downwards, and because of the high frequency of this vibration, over I cannot observe clearly the position of these strings, and due to the continuation of the pulses we can observe this particular formation of the loop, and this wave can be seen as we have observed on this board. So that's why it is called the stationary wave, because we can observe the loop, not the individual position of the string. That's why it is called the stationary wave. And now at the fixed end, node will be formed here, and at the middle position where the amplitude is maximum, this position is called antinode, where the energy is also maximum. So if we describe the phase difference between the particles existing in the loop here on the string, these are the same phase particles because they are moving simultaneously from the same position. And if we generate the two loops, for example, in the same string, we will plug this string middle of the middle position. From middle of the middle position, for example, it is a midpoint, and it is a midpoint on the left hand side of the half of the string, and we are plugging this string or the rubber band from this position, and when we release it, when we plug it at the time t is equal to 0, the position of the string will be here, and this particular wave will be formed at the time t is equal to 0. And when we release it, this loop will move vertically downwards. At the same time, the crest of this loop will be moved on the in the upward direction. So the new position of the wave will be this one, this blue wave, and this wave is formed because this string is moving with a very high frequency, which cannot be observed by our eye. So we can see only the loops formed in this wave. That's why it is called the stationary wave. Okay, and we have nodal points where the amplitude and energy is 0, and we have the antinodes here. For example, these 2 points are the antinodes. And now we'll discuss about the movement of the particles. For example, at the time t is equal to 0, all of the particles are on the black wave here. For example, we are considering 4 particles in the first loop and the 4 particles on the second loop. Now after some time, when we release it, these all particles will move in the first loop vertically downwards simultaneously, and these all particles will move vertically upwards in the second loop. So these particles, for example, P and Q are same phase particles because these are on the crest position, and particles R and S are the same phase particles because they are on the trough positions, and P and Q particles are moving with the same speed in the same direction. So that's why they will move downwards, and particles R and S will move upwards. So we can say that in the next position, the particles P and Q will be here, and after some time the particles R and S will be here. So particles, if we describe the phase difference between particle P and R, they are in the 180 degree of phase difference because P particle is on the trough position and R particle is on the crest position. So they have the 180 degree phase difference, and they are moving simultaneously from crest to trough and from trough to crest. So that's why we can write here P and Q are same phase particles, and R and S are also same phase particles, but P and R are out of phase particles, and they have the 180 degree phase difference between them. Okay students,